Thanks for reminding me, Aiden. Entertain the 8th graders. They'll be excited. I know. You got to do it again. I'm not sure. There'll be some that didn't come. So it'll be new to them. The others can be leaders. Okay. All right, y'all. Let's see what we did. Okay. Bye-bye. So if we look at this first one, did they give me the 0 term in my graph? Yeah, they did. Yeehaw! All right. So a sub 0 is 8. What's my slope going to be? -2. So my common difference is we're going down by 2. And so if we write our expression, a sub n would be 8 minus 2n. Okay? And so if we want a sub 17, we could just plug that in. 8 minus 2 times 17 and -26. All right, rock and roll. Okay? So that one pretty straightforward. They gave me the graph. They gave me the 0 term. We can write it. Life is good. Okay? Slope, intercept is right there. All right? But now let's look at the next one. Okay? Let's look at the next one. This time they give me the 2nd term and they give me the 6th term. How are we going to find the common difference? Find the rate of change. It's slope. Okay? It's slope. So we're going to take 9 minus 7 over 6 minus 2. It's just our rate of change. It's slope. Okay? And so if we do that, that gives me 2 over 4, which is 1/2. Now, we still do not have the 0th term. And just because that rate of change is 1/2, I don't want to fool with finding it. Okay? If it was 3, I'd go about my business and get it. Okay? So let's do point slope form. All right? Does it matter which one of these two terms I use to write it? No. Okay? So we're going to take our common difference, n minus, the term was 2, and then plus 7 is probably what I would have done. You could have put 6 in there with the n and then the 9 at the end. Okay? Either one of those would have worked. All right? So then to find the 24th term, we can plug it into what we've got right here. A sub 24, 1/2 times 24 minus 2 plus 7. All right? Which would give me 18. Okay? I think the thing that makes it difficult for us with arithmetic and geometric sequences is we get so focused on, oh, there's this arithmetic formula. It's a linear equation. Write the linear equation. Okay? If you write the linear equation, it is what it is. Okay? Slope is the difference. Right? N is my x. Y is that term that we have. Okay? What questions do you have about arithmetic sequences? Okay. All right, let's move on to geometric. Obviously, geometric sequences can't be the same. Okay. How does a geometric sequence change? Do you remember? It's multiplying. Okay. It's multiplying or dividing. All right. So we're going to multiply or divide to get to the next term. All right. And we refer to that as a common ratio. Okay. As a common ratio. So when we're dealing with our geometric sequence, they have a common ratio. And because they got super creative, they use R to represent that. Okay? Just like for common difference, they use that D. All right? So they have a common ratio. Right? Now, what that means is we are either multiplying or dividing. All right? If it's division, they use a fraction so that it's always multiplication, okay? The way we're going to refer to it is that they have a constant proportional change, right? So know that in AP, we have to write reasons. And so one of the ways or one of the phrases that we will use to justify things as geometric is that constant proportional change. It means we're multiplying by a whole number or we're multiplying by a fraction, right? So let me give you that basic formula, Okay, G sub n. Start with G sub 0 times R to the n, R being the common ratio. Again, G sub 0 is the 0th term. Okay, not the first term that we see, but the 0th term. And if I don't have that term, we can write it, right, using the term that we have, R to the n minus k. Where G sub k is the kth term. What kind of function are we creating here? When it was arithmetic, we had linear. What do we have for geometric? Not quadratic. It's exponential. Good, it's exponential. All right? Because your variable is the exponent. That's why it's exponential. You're about to get that orange peeled? I could tell. We're going to have to take a lesson in orange peeling. Yeah. There's paper towels back there on the back corner if you need one. All right, by the green cabinet. Bless. All right, let's take a look at this one together. All right, so we've got the sequence 3, 6, 12, and 24. Is it geometric? Yes or no? Okay. How is it changing each time? We're multiplying by 2. Okay, so we're multiplying by 2. So my R is 2. Okay, so it's a yes. We're multiplying by 2 each time. Now, could we find the 0th term? Okay, if going forward, I'm multiplying by 2, what am I going to do to go backwards to get the 0 term? Divide by 2. And so what's 3 divided by 2? 1.5, or let's just call it 3 over 2. Okay? I avoid decimals like the plague. Okay? So improper fractions are good for me. So now let's write a rule. Okay? We know the 0th term. We know the R. So 3 over 2 times 2 to the n. Okay? It's that simple. If you know the 0th term, okay, what is that? Value times your initial value times your rate. All right. What will we do to get the 10th term? Phone a friend. What would we do? Plug in 10. Okay. And I hope we've got a calculator. Right. What'd you get? Yep, 1536. All right. So this time it says write a new rule. Okay, write a new rule using the first term of 3. Okay, and so here's the nice thing about this. To me, these are much easier than the arithmetic ones. You start with the term you know, it's 3, times my common ratio, n minus whatever term they gave me, which was 1. All right, it's just the simplest way to put it in there. 3 times 2 to the n minus 1. Right. And then if we graph those points that we have, okay, so 1, 3, this one's a little bit harder to do, 2, 6, and so on. Okay, 3, 12, oops, and then 4, 24. What do you notice about that? It's curved, okay? So it's definitely curved. It's not linear. Okay. And in fact, it represents our exponential growth, okay? You told me earlier that we have exponential growth when our base is greater than 1. Our base is 2. Our ratio is 2. It's greater than 1, so it's growth. Okay, so you told me that when we started. Okay. So let's look at a couple more things. Okay. Okay. All right, check this one out. All right, here's the one that's got some fractions in it. We're going to think about it a little bit. Okay. Arithmetic or geometric? It's geometric. Okay, what are we multiplying by each time? It's dividing by 3, so that as a fraction would be 1/3. Yep, we're multiplying by 1/3. Good. Yep, we took 5, we divided it by 3. We divided by 3 again, we get a 9 in the denominator. Divide by 3 again, we get a 27. Okay? So, all right, couple of options. All right, they did not give me the 0th term, and that's okay. All right, they gave me the first term as 5. What would my equation look like if I use that first term? What happens to my exponent? Okay, what term did I use? First term, so n minus 1. That's perfectly acceptable. Okay, they gave you the first term. We put it down as our initial, as where we're starting. Okay, we keep our common ratio, subtract that number of that term from your exponent. Now, could we have figured out the 0th term? Yeah. Okay, if I was dividing by 3 going forward, what would I do to go backwards? Multiply by 3. So a sub 0 could have been 15. So we also could have used this. 15 times 1/3 to the n. Okay, so either one of those is the correct answer. All right, either one. Okay. All right, so now this is interesting. Is the domain of the function, all right, so the function would be y equals 15 times 1/3 to the n, the same as the domain of the sequence? The sequence are those individual terms that we have. What do you think? Interesting question. Okay. When we do a sequence, these are finite terms. So even though we connected the dots earlier, are the dots really connected? No. Okay? It's finite. All right? So when I have an exponential function over here, my domain is everything. Negative infinity to positive infinity. We're good. All right? But when we have a sequence, okay, n represents specific things, all right? It represents our terms. And so our domain would be 0, 1. We wouldn't have a negative, right? We wouldn't have a negative term, so on and so forth, all right, until we got to n, all right? So that's the difference, all right? The function has an infinite domain. The sequence has a finite domain, all right? So the difference there. Does this function have a growth rate? Is it exponential growth? No, it's exponential decay, right? So let's change that. That should say decay rate. All right. How much is it going down each time? 1/3. It's 1/3. So just looking at some differences there. Okay, looking at those relationships. All right, see if you can do number 7. Can you write the equation? Okay, did they give me the 0 term on this one? Yep, it's proper. 8. 0, 8, 1, 4, 2, 2, 3, 1. Okay, so we probably got enough right there. What are we doing each time? Divide by 2. So what's my R? 1/2. Okay, so they gave me that 0 term, so we could write it as G sub n equals 8 times 1/2 to the n. I don't have to do anything fancy because I have the 0 term, right? And if we want to find the 10th term, we're just going to plug in 10. Okay, so 8 times 1/2 to the 10th, right? Probably get a crazy decimal. Do you know how to change it back to a fraction? How we do that on the calculator? Math, enter. Yep, math, enter. Magic 3, that's what I always call it. Bless you. Okay, so 8 times 1/2 to the 10th. If it doesn't give you a fraction, if it gives you a decimal, math, enter. Okay. Okay. Now, let's talk about 8. 8's where it gets interesting, okay? 8 and 9. Right? Because things just aren't quite as straightforward. This isn't like a linear function where I can just do slope, okay? This is exponential, so it's a little bit different, okay? So it says let G sub n be a geometric sequence with G of 3 is equal to -2 and G at 6 is equal to 128, okay? What do I need to find? Because I've got some values here, but what do I not know to be able to write the equation? I don't know the 0 term, and I don't know R. Okay, so we've got to find R. So let's start with this. Let's use our G to the 6th term. You could have started with a G to the 3. It doesn't matter, G sub 3. So if I'm going to write an equation for G to the 6, okay, it's going to equal my, well, here, let's do this. I'm going to go backwards. Hold on a minute. Okay, let's do it this way. So G sub n would equal, okay, if I start with my G sub 3 term, okay, it is -2, okay, R I don't know, but what's my exponent going to be? N minus 3, okay, because I started with the 3rd term, okay, I started with the 3rd term, thank you. So if we wanted to use the other ordered pair, which we're going to do, hey, what you doing? How did it go? Oh, okay. All right. It's all good. It's all right. I left your stuff back there. Okay.
Thank you.
You're welcome. So let's plug in this 0.6. We've already used 3 and -2. Let's plug in 6 and 128. All right. Let's see if we can find R. All right. So let's do that. G sub 6, bye, y'all be good, would be 128 would equal -2. R is what I'm looking for to the 6 minus 3. Okay, so we're going to simplify it, see if we can solve for R. All right, so 128, -2, that would give me R to the 3rd. Now, how am I going to solve that equation? Yeah, we're going to take a cube root, but what do I need to do first? Yeah, divide by that 2. Yeah, divide by that 2. It's going to make your life a little bit easier. If we do that, that's going to give me, come up here, -64 equals r cubed. And you're right, we have to take a cube root of both sides. And so what's r going to equal? Be a negative 4 because it was a negative 64. Okay, so we used a cube root. Now, let's go back to that original purple equation. Okay, we can leave everything the same, but now I know what r is. Negative 2 times negative 4 to the n minus 3. All right, so we do what I like to call nifty substitution. All right, write an equation using one of the points, plug in the other one to solve for r. Okay, then put your r back into that original equation you wrote. Now, we still haven't finished the problem, because what did it want me to find? Yeah, the 11th term, g sub 11. So the 11th term, negative 2 times negative 4 to the 11 minus 3. It's a big number, or small, depending on how you look at it. All right, so using what we just did, okay, let's try number 9, okay? It's about rumors. This reminds me of freshman girls. Okay. A wild rumor is spreading that Mr. Passwater won 3rd place in the World's Strongest Man contest. Mr. Passwater probably didn't start the rumor, okay? Says the number of people that have heard the rumor can be modeled using a geometric sequence where 43 people had heard the rumor on day 3 and 140 people have heard the rumor on day 6. According to the model, how many people to the nearest whole number have heard the rumor by day 10? All right, see if you can do that one. All right, did you start like this? Okay. Our general form, right? We take that first one, day 3, we had 43 people who had heard it. So G sub n, 43, r to the n minus 3. So that gives me 2 variables. It's too many. All right, let's plug in the next term and see if we can figure out what r is going to be. Okay, so if I plug in G sub 6, that would be 140 equals 43 times r to the 6 minus 3 over 140, 43 r to the third. So just like we did a few minutes ago, okay? Now, 140 over 43 is not pretty, okay? And it equals r to the third. And then when I take a cube root, it's even uglier, okay? It's 1.482, okay? Right? Do you remember how to do a cube root on your calculator? It's under math. Good. Okay. What if you forgot that? What's another way you could do it using the exponent key? No? That makes it going 1/3. Good. Good. It was a fraction. 1/3. All right. So now we've got our r. If we plug everything back in, and then so g sub n equals 43 to the 1.482 times n minus 3. And we want to plug in a 10. All right, G sub 10. Did you get about 676 people? Okay. So we just plug it into what we had. All right. Good. Good, good, good. For some reason, people seem to do better with the geometric than they do the arithmetic, and you've been doing the arithmetic ones for much longer. Okay? But I think it's just the way it's written. I don't know why, but it feels, for some people, just a little bit tougher. Okay? So this is what we had already said. This is the same thing as slope-intercept. This is the same thing as point-slope. Okay? All right, so we'd already said that. Those were our linear functions. Okay. So just as a reminder. Okay. And then on the next one, we look at the geometric sequences and how they relate to exponential functions. So this is how these look. All right. This is your general exponential, okay? Y equals a times b to the x, right? Which you're used to seeing, okay? And this one, if we use a point, y1 would equal our base times x minus x sub 1, okay? So it's the same thing, all right? It's all what you've been doing, right? With linear and exponential functions. So this next box, okay, put a star right here. This is what we're going to use when we have to write a justification. Okay, so this is what it's going to be expecting in terms of our terminology when we do a justification for something being linear or something being exponential. Okay, right, and here's the important part. For a linear function, all right, our justification over equal length input value intervals, the outputs change at a constant rate, okay? So what that's telling me is I have a constant rate of change. That equal length input is important, okay? So over equal length input value intervals, the output values change at a constant rate, all right? And so what we're saying here, that's just like an arithmetic sequence, okay? The change in m in y is based on addition. Okay, so it's like your arithmetic sequence, right? When we get to exponential functions, okay, this is where we talked about initially that that rate of change is proportional. But again, we have to start with over equal length input values, okay? So my x's change equally, the y values change proportionally. Okay, it's based on multiplication. Okay, just like our geometric, right? Because here's the thing. If they say, is this linear or exponential? And you go, it's linear because I added the same thing every time. They are not going to give you the points, all right? You're going to have to make the justification statement. So what I want to do is just talk about, do a couple and let's write the statement so you've got some there to look at, okay? You've done the hard part of this so far, right? So let's take a look, right? The first thing that I look at are my x values. Do they change by the same amount each time? Okay, so check that. Are they changing? Are they equal length? All right, are my x's changing by the same amount? Yes, okay. So we've met that qualification, all right, for linear or exponential. They are changing, all right, at equal lengths. Then we look at what our y values are doing, okay. What are we doing each time here? We're subtracting 2, okay. So is this linear, exponential, or neither? We would say this is linear because over equal length input intervals, the outputs change at a constant rate. Okay, now, unlike in calculus, they are very specific, all right? They give us, down to the wire, exactly what you need to say to get the points in the free response section. It's really nice, okay? Also, they tell you exactly what's going to be on every free response question, all right? So you know free response questions 1 is going to cover these topics in this order. It's beautiful, okay? They don't do that in calculus, all right? But in pre-cal, they do, all right? Check the next one, all right? What are you going to look at first? X's. Are they equal length between each x? Yeah, they are. Okay. So now look at your y's. Okay. What do we think? Right. This changed by 1. This changed by 3. That changed by 5. That changed by 7. Okay. So does it meet the qualifications for linear or exponential? Okay, we didn't add or subtract the same thing. We didn't multiply or divide the same thing. All right, so we would say neither. Okay, because, and you start that sentence again. Over equal length input interval. Oh, like it's just a lot. Okay, the outputs do not change at a constant rate or proportionally. Okay, I probably misspelled that. The good thing is it's not a spelling test. Okay, as long as you get close, they'll know. All right, try the last one. What are we doing on this one for the y values? The x's are good. Yeah, we're dividing by 2. Okay, we're dividing by 2. So the proportion there would be a what? 1/2. Okay, so this one is exponential. All right, because over equal length input intervals. You get the point, right? The outputs change proportionally. Okay, so that's the words they're looking for. Okay? All right, last one. Sometimes they might ask us to do some comparison, all right, between two different situations and figuring out what's going on. All right, so it says to imagine that two fast-growing vines that sprouted from Jack's magical beans. When you begin measuring the vines, they're both 10 feet long. Okay, for the next 4 days, vine A's length increases 50 feet each day, while vine B's length doubles each day. Okay, how is vine A growing? It's linear, it's arithmetic. Okay, so we would say linearly. Or let's just say linear, I can spell that. All right, and then how's vine B growing? Exponentially. Okay, so it says define a function f to represent vine A's length in terms of the number of days t since vine A was 10 feet long. Okay, so a function f, it gives you a variable, you want to use it. Okay, so f of t, right? What would that equation look like? Yep, 10 plus 50t. Okay, 50 was my rate of change. Okay, it said feet each day or feet per day, so that was my rate of change. And I started at 10. Okay, it asked me to do the same thing, a function g of t that would represent vine B. Okay. So if it's doubling each day, if it's exponential, what would that look like? Yep, 10 times 2. We're using t's. So to the t. Okay. All right. Then it gets pretty straightforward. Which vine will be longer 3 days after the vines are 10 feet long? Okay, in other words, when t equals 3. All right. How are we going to get those? Plug them in for good. Plug in 3. Okay. So if we do our comparison, all right, which one's longer? Vine A is how much longer? Okay, so it's 120 feet longer after 3 days. All right. What about after 30 days? Yes, baby.
If it's 160 and 80, wouldn't that be 80 feet long?
Yep. Uh-huh. I don't know why I said 120 for fun. Subtraction, not important. Thanks. Okay. I don't know why. I said 6 and 8 and I thought 2. Right? Got life. Okay. All right. Which one will be longer after 30 days? Just think about it. What do you think? Vine B. Why? It's exponential. It's growing much quicker. Okay? So the exponential function is growing much quicker. So we could say that after 30 days, right? And we just know that vine B will be significantly longer. Good. Okay, significantly longer. And then it says, how many days does it take vine B to overtake vine A? How could we figure that out? Yeah, where are they equal to each other? Okay, and this is where it says calculator. All right, We take our f of t, put it in y1, our g of t, put it in y2, and find that intersection, okay? So, just for the sake of time, all right, we're going to skip that part, all right? But that's what we would do, okay? And it's about 4.58 days, by the way. Okay. Now, if vine B's length grows only 5% each day instead of 100% where it's doubling, will vine A ever become longer than, or will vine B ever become longer than vine A? How is that going to change vine B's equation? If it only grows by 5%. Instead of doubling where I had a 2. Okay, so we've got a 0.05, right? But we got to keep it because it's got to be greater than 1, remember, because it's growing. All right, 1.05, all right, to the t. All right, so we would change our g of t and then set that equal to h of t and find your intersection. I mean f of t. I don't know why I said h. Okay, all righty, good job. All right, the answer's 134 days. Okay. So if you're not sure you remember how to do those intersections on your calculator, do that. All right, tonight, play with that. Your lesson practice, there's 2 of them, okay, because we did 2 sections, 2.1 and 2.2, okay. Here are the ones to look at, 2, 4, 8, 10, 12, 14, 15, 17 on the first, okay, and then 1, 3, 4, 5, 6 on the second. You can skip your wrap up today just because of time, okay? So we worked all the way. Play tomorrow, so practice these tonight, okay? Because you'll forget if you don't. All right, while it's fresh on your brain.
I'll just stick it in the trunk. Can't believe it.
Go get your phones. We'll have the best time. Okay. We'll miss you. Yeah, don't forget your phone. See you, bud.
Anna Jones, come to the main office real quick for a second. Anna Jones to the main office for 1 second.
Okay, okay, all right. I'm gonna let you watch Algebra 2, since that might be good.
Okay.